Finding the force on objects at depth. So here's our question. How much force is on a 2 meter by 10 meter rectangular metal plate standing upright at the bottom of the Mariana Trench, which was explained. The Mariana Trench was talked about in a previous video. So here is your plate standing upright. So the problem is that we don't have constant depth on that object. So we need calculus. So the density of the seawater was already given in the previous video to be this. Of course, the gravity is this. The depth of the bottom, all the way to the bottom of the Mariana Trench, was this amount of meters. So our strategy is we're going to go down to this depth here and figure that on a delta y strip of area across there, that depth is essentially constant there. So we're going to then find a force on that area strip, and that area strip is 2 wide by delta y high, and then we're going to add all those forces up. Okay, so we need to know the depth at the y location right here. The depth at the y location would be all the way to the bottom minus off the y coming back up, as long as we're counting this way. Y equals 0 on the floor to y equals 10. You could do it the opposite way. So the pressure there at that y location is your density, your depth, and the gravity. That's newtons per square meter. The area that we're talking about is 2 delta y, so the force in the strip is pressure times area, and so that's your pressure right here and your area right there. So the total force in a Riemann sum as y values goes from 0 to 10 is all this just multiplied together. Then you multiply the various numbers together and you get this integral. And then I factored out this constant. Integrated, get your y and your y squared over 2. Evaluate from 0 to 10. Plug everything in. I went to step right here, put the decimal place here, and multiply by 10 to the fourth in order to get a 10 to the fourth and 10 to the fourth. So I could add the two, or actually subtract the two front numbers in terms of the 10 to the fourth. And then I put the 10 to the fourth back on, and I have this many newtons of force on that plate. So the question is, can we do this problem in British units? And the answer is yes. So what we do here is we're going to convert. Okay, so we have 6.8 miles is 5,280 feet per mile. So that's the depth down to the bottom of the Mariana Trench. So that's about 35,904 feet depth at the bottom. The density of the seawater, 1,027 kilograms per cubic meter. Converting that, that's 64.1 pounds per cubic foot. Could be a little bit of error there in the conversion, but it's okay, we'll take it. Now, the important thing to note, when you're in the British system, the foot-pound system, pounds is weight, already has gravity accounted for. The 32 feet per second squared is already incorporated into the pounds. So we don't need the 9.8 factor. So that's the big difference. So the metal plate was 2 meters by 10 meters. That's about 6.56 feet by 32.8 feet. We're getting a little error there. That's okay. Pressure on the delta Y strip is the 64.1 density times the depth down there, which is 35,904 minus the Y coming up short of the bottom, and that's pounds per square foot. The force on the delta Y strip is then that pressure times the area, which is 6.56 times delta Y pounds. So the force is Y equals 0 to 32.8. So then you add up all those forces on those delta Y strips, right as a Riemann sum, but we already did that for the previous one. We'll just go straight to the integral, multiply the numbers. You got this dy around the Simpson 100 program. Maybe got a little error there, but anyway, I got this amount of pounds, and I did a quick check. The original Newton's answer was this, and the pounds conversion of that is this, which is, this is 494, this is 493. I think we just got a little error in the different processes that we did there. Normally when you do a problem, you don't convert it from the SI international units over to the pounds British system. You just do the whole problem in the British system, one or the other. So bottom line, close enough, we'll take it.